Welcome to this explainer. Today, we're tearing down the absolute foundational building blocks of computer programming. We're going to start with basic sequential logic and build all the way up to complex, nested decisions. So if you've ever found yourself wondering how on earth a computer knows exactly what to do and when to do it, you are in the perfect place. Let's get right into it.
Here's our roadmap for the day. First, structuring solutions. Then we'll hit sequential logic structure, followed by the solution development steps. After that, we'll dive into an intro to decision logic, step it up with advanced decision logic, and finally wrap up with some key rules and a quick recap.
Section 1. Structuring solutions. Okay, before you even think about writing a single line of actual code, it is absolutely crucial to understand how to mentally map out your solution. Think about it. The whole goal of a computer is to solve problems and ultimately make us more productive. You hit that peak efficiency by taking a giant, intimidating problem and slicing it down into smaller, totally manageable pieces we call modules. Inside those modules, you rely on three main logic structures: sequential, decision, and loop. By breaking things down this way, you completely eliminate the headache of rewriting the exact same processes over and over. Plus, you really want to prioritize readability here, so use proper naming for your variables and keep your indentation clean. Just look at how clearly these flowchart diagrams separate our tools. You've got the sequential structure, which is just a straight, uncomplicated path straight down. But then compare that to the decision and loop structures. See how they introduce those diamond shapes? Those diamonds are super important. They represent branching paths where the program literally has to make a choice or repeat a process. Section 2. Sequential logic structure. Let's start with the simplest, most commonly used building block of them all. Sequential logic is exactly what it sounds like. It's processing a set of instructions strictly in order, right from the very top to the very bottom of an algorithm. Honestly, every single problem uses sequential logic to some degree. It's essentially the baseline structure that works hand in hand with the more complex ones we'll look at later. Take a look at this flowchart for a simple program that just handles a user's name and age. You can see how the processing flows perfectly straight. It starts at the top at that flattened ellipse, flows directly into a parallelogram that tells it to enter name, age, then drops straight down to another parallelogram to print that data, and finally, it ends. No deviations, no questions asked, no choices made, just pure top-to-bottom execution. Section 3. Solution development steps. Now, to actually implement these logic structures in a real-world scenario, you've got to follow a pretty rigid framework. These are the 7 vital steps of solution development. They guide you all the way from your initial problem analysis charts, where you're figuring out your inputs, processing, and outputs, through coupling diagrams, right down to drafting your pseudocode. Pseudocode, our final step here, is basically a generic language representation of your algorithm. Think of it as the bridge between your flowchart and the actual coding language you're eventually going to use. But here is a huge point to remember. Step 7 isn't just about writing that pseudocode. It inherently requires you to test that solution to catch any errors in logic or calculation. Seriously, never skip the testing phase. Charts and diagrams are awesome for development, but let's be real. They're rarely perfect on the first draft. You absolutely have to verify your logic before committing it to code. Section 4. Intro to decision logic. Once you've got those sequential steps down, it's time to give your program a brain. It's time to let it make choices. So ask yourself, what happens when a program can't just go straight down? What if it needs to choose between 2 or more entirely different actions based on what the user inputs? Well, without decision structures to evaluate true or false conditions, a computer would just be a ridiculously fast calculator. Decisions are what actually make software dynamic. Here's the basic anatomy of a decision block. In flowcharting, as we saw earlier, we represent this with a diamond. Inside that diamond is a condition, basically a question the computer is asking. Based on the answer, it creates one specific flow line for a true result to run one set of instructions and a completely separate branch for a false result. And remember, there can never be more than 2 flow lines coming out of a decision block, because a condition can only ever evaluate to true or false. There's no maybe. Let's look at a really practical, totally exam-relevant example. Payroll. In this single condition flowchart, we're checking if an employee gets overtime. The diamond asks, are the hours greater than 40? If that's true, the logic branches off to calculate time and a half. But if the condition is false, it just drops down the other branch to multiply the standard rate by the hours. It's simple, it's elegant, and it perfectly controls the flow. Section 5, Advanced Decision Logic. Real-world problems, as you probably guessed, rarely rely on just a single condition. So let's talk about multiple conditions, nested instructions, and optimizing our logic flow. Notice how things start building in complexity here? When logic requires one decision to be embedded inside another one, kind of like nesting baskets, we use nested if-then-else instructions. This flowchart illustrates it brilliantly. It checks if an employee's pay type is hourly first. Only if that is true does it step inside the nested decision to check if their hours are over 40. If they aren't hourly to begin with, like say they're salaried, the false branch skips that overtime check entirely. It's a highly efficient way to route your logic. But what if conditions aren't dependent on each other at all? That brings us to straight-through logic. This is where all decisions are processed sequentially, one after the other, regardless of what happened in the previous outcomes. Now, because it tests every single condition unconditionally, it's actually the least efficient logic type. But it is absolutely required when you have conditions that are entirely independent of one another.
Let's compare efficiency real quick. You've got the inefficient straight-through logic for calculating concert ticket prices based on age. Even if the person is under 16 and we already know their charge is $7, the program still wastes processing power checking if they're between 16 and 65 and if they're over 65. Contrast that with positive logic. Positive logic strategically stops processing other decisions the second it finds a true condition. If the person is under 16, boom, it sets the charge to $7 and immediately drops out of the entire block. It is so much faster.
So, just to firmly define these two optimized types, positive logic continues processing through the module when the resultant is true, skipping remaining decisions. This perfectly aligns with how we naturally think. Negative logic is similar but continues processing only when the resultant is false. Quick tip for your upcoming assignments: negative logic is widely considered the hardest to write and understand. It forces the flow to continue on false results, which can so easily introduce errors if you aren't tracking your flow lines super carefully. And that brings up a massive rule for your pseudocode. This sales commission flowchart uses positive logic, but look closely at the pseudocode. It highlights a crucial readability rule. Always, always use proper brackets and indentation. When you write nested if-then-else instructions, you literally must indent the true and false actions to show the nested levels of your decision structures. Without proper indentation, you, and whoever is grading your work, will instantly lose track of which else belongs to which if. Section 6. Key rules and recap. All right, we've covered a ton of ground today. Let's recap the core takeaways and specific programming patterns you need to lock into your memory. First up, when you're analyzing financial logic problems, remember that you have to clearly define your variables. Take the standard compound interest formula, for instance. Your inputs must distinctly track the principal amount, the interest rate, the number of years, and crucially, the compound interval. Missing even one of these variables in your problem analysis chart is going to completely break your sequential logic down the line. Next, consider this summary table your ultimate cheat sheet for exam prep. It perfectly compares the flow behavior and efficiency of the logic types we've just decoded. Just remember, sequential is your baseline. Straight through checks everything and has the lowest efficiency, but you need it for independent conditions. Positive logic skips unnecessary checks when true, making it super efficient. And negative logic skips on false, making it useful but incredibly complex to route. We'll leave you with this final thought. Now that you truly grasp the rules of sequential and decision logic, how are you going to diagram your next coding problem before you type a single line of syntax? Remember, a well-planned flowchart and structured pseudocode using these exact frameworks will literally save you hours of debugging. Keep these building blocks at the front of your mind next time you tackle a complex problem. Thanks for joining this explainer, and happy problem solving.